When we talk about the C programming language, we are talking about the bedrock of modern computing. It is everywhere. It runs the operating systems, it drives the embedded devices, and it powers the high-performance applications that define our digital infrastructure. But for all its dominance, C has a reputation for being unforgiving. It is old, it is raw, and when you try to build a tool to read it, a compiler, the challenges multiply. For decades, the standard approach has been to write compilers in C itself, or to lean heavily on massive frameworks like LLVM. But in 2025, the landscape is shifting. We are seeing a new wave of developers asking a different question. Can we build a C compiler using Zig? And more importantly, can we make it robust, safe, and reliable in ways that previous attempts have struggled to achieve? Here is the thing about writing a compiler in 2025. It is no longer just about parsing syntax. Anyone can write a parser that reads code and spits out an abstract syntax tree. The real battle is in the details that happen after parsing. It is in how the compiler handles mistakes. It is in how it manages the memory of the compiler itself while it builds the machine code for another language. And it is in the debugging information it produces. If you want to build a production-grade tool, you cannot just focus on the happy path where the code is perfect. You have to plan for the messy reality of real-world software. Zig offers a unique opportunity here because of how it handles memory. Unlike C, which gives you raw pointers and hidden allocations, Zig forces you to be explicit. It does not have a garbage collector that hides behind the scenes. This makes it an ideal host language for a compiler that needs to be fast and predictable. When you write a C compiler in Zig, you are building a tool that understands the low-level constraints of C but benefits from the safety checks of a modern language. This allows for features that were previously too risky to implement. For instance, you can write checks that ensure the compiler itself does not crash when it encounters malformed input. Consider the problem of error recovery. In a standard compiler, if you hit a syntax error, the program might panic. It stops. It gives up. But in the real world, developers do not write perfect code. They write code with typos, missing semicolons, and mismatched brackets. A robust compiler needs to keep going. It needs to try to understand the code around the error so it can report other issues without stopping the entire process. This is often called token synchronization. Imagine you are reading a book and you stumble over a word that does not make sense. You do not stop reading the whole book. You skip ahead to the next sentence and try to understand the context. A compiler needs the same instinct. In 2025, the focus is on implementing recovery strategies that allow the compiler to resynchronize at statement boundaries or block boundaries. This ensures that a single typo does not cascade into hundreds of confusing error messages. Now consider memory safety. When you are building a compiler, you are writing a program that reads text and writes binary. This process involves allocating memory for thousands of nodes in the syntax tree. If you manage this poorly, you get memory leaks or buffer overflows. Zig allows you to define exactly where memory lives. You can use stack allocation for temporary data during parsing and heap allocation for the final output. But beyond just allocation, Zig allows for comptime execution. This means you can run code while you are compiling the compiler. You can validate types and structures before the compiler even starts running the target code. This adds a layer of safety that is hard to achieve in traditional C compilers. It means that if your internal data structures are wrong, you find out at compile time, not at runtime. This leads us to debugging instrumentation. A compiler is not just a translator, it is a tool that helps developers understand their code. In 2025, the expectation is that a compiler provides rich debugging symbols. It needs to map the generated machine code back to the original source lines. It needs to track variable lifetimes and types. Zig makes this easier because it has built-in support for metadata. You can attach information to your data structures that the compiler can later use to generate debugging files. This is crucial for modern development environments where developers rely on breakpoints and variable inspection. By integrating this instrumentation directly into the compilation process, you ensure that the debugging experience is seamless. The developer does not need to run a separate tool to get symbol information. The compiler handles it as part of the standard build. There is also a significant shift in how we approach the scope of a C compiler in 2025. The research indicates a move towards modular and subset-based architectures. This means developers are not trying to support every single feature of the C standard immediately. Instead, they are building modular components that can be extended. This is particularly relevant for resource-constrained environments. If you're building a compiler for a small embedded device, you do not need the full weight of the standard. You need a subset that is reliable and fast. This modularity allows for better error recovery because the parser is not fighting against the complexity of legacy features. It focuses on the core logic that matters for the specific use case. Furthermore, we are seeing advancements in parallelism. Zig is now being used to integrate pragma-driven shared memory parallelism. This refers to OpenMP loop directives. By supporting these directly, a Zig-based C compiler can optimize loop-heavy workloads without external runtime overhead. This is a significant performance boost. It shows that Zig is maturing as a platform for high-performance computing. It is not just a niche language anymore. It is competing with established systems for speed and efficiency. This capability suggests that a C compiler written in Zig can handle the demands of modern software engineering, including the need for parallel execution and multi-core processors. The narrative around C and Zig is evolving. It is moving away from the idea of replacing C entirely. Instead, we are seeing a pragmatic approach where Zig acts as a modern, safer backend for C compilation. This bridges the gap between legacy codebases and modern systems programming needs. It acknowledges that C is not going away. It is too entrenched. But it also acknowledges that we can do better than the tools we have today. We can build tools that are safer, faster, and more reliable. The key takeaway from the current landscape is that reliability is the new frontier. It is no longer enough to just generate code. You must generate code that can be debugged, maintained, and trusted. The tools of 2025 are designed with this in mind. They prioritize error recovery so developers can keep working through mistakes. They prioritize memory safety so the tools themselves do not become a source of instability. And they prioritize instrumentation so that the output is useful for the entire development lifecycle. This shift represents a maturation of the field. We are moving beyond the excitement of building a compiler from scratch to the discipline of building one that works in the real world. Whether you are targeting high-performance computing, embedded systems, or general-purpose development, the principles remain the same. You need to handle errors gracefully. You need to manage resources carefully, and you need to provide feedback to the developer. Zig provides the foundation for this. It gives you the control of C with the safety of a modern language. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.